The last algorithm for finding a minimum spanning tree that you'll see is Baruvka's algorithm. Now, both Prim's and Kruskal's algorithm use a priority queue, and with Baruvka's algorithm, we'll see that we don't need a priority queue or any other separate data structure like a cloud to keep track of different connected components. Now, it works similarly to Kruskal's in the sense that it grows many clouds at once and always chooses a minimum weight edge to connect those clouds. So the idea is we'll maintain a forest, T, on which an edge can be added in constant time with an adjacency list. And we add an edge a total of big O of n times, n minus 1 times exactly. Now, rather than maintaining separate clouds with a different data structure, because T is a forest, we'll find all the connected components of T. We've added some edges to T already. This will become, when we're finished, our minimum spanning tree. But until then, we can find, using a depth first search on T, all connected components of that tree. So we can find connected components in linear time using DFS, and then label vertices based on which connected component they belong to. Then we'll process each connected component and find what is the smallest weight edge connecting two different components. So in total, big O of m time, we can find the smallest weight edge connecting two different components by scanning all edges incident to a vertex in that component. So then the total running time for one round of this is big O of m time. This includes the depth first search to find connected components, for relabeling vertices, finding all minimum edges connecting two different components. But the number of rounds that we do is log n. So in each round, we choose one round being one iteration of this while loop. In each round, we choose one edge pointing out of each cluster and merge it into a new cluster. So in each round, the number of clusters is reduced by half. So the total number of rounds is log n. So let's see this on an example graph. So we're going to maintain, here are all of the connected components of T. And for each connected component, we'll check to find the minimum edge going out of that connected component. So both SFO and LAX airport, they'll find, oh, this edge, 337, is the smallest weight edge coming out of this. And it's also the smallest weight edge coming out of this one. DFW will find this edge 802. ORD will find this edge 621. BWI will find this edge 184. That's the same edge that JFK will find. BOS will find this edge 187. PVD will find this edge 144. So, for example, each connected component finds what are all of the edges coming out of this connected component, and then keep track of this is the smallest edge coming out of this connected component. So some connected components might find the same smallest edge connecting them, and some of them will find different ones. But within that first round, we'll go through every connected component that we have and add the smallest weight edge associated with it. So these arrows are just indicating 802 was the smallest edge coming out of DFW, and it was also the 621 was the smallest edge coming out of ORD. 337 was the smallest edge coming out of LAX, and also for SFO. So after that first round, now we have only two connected components. This one in blue here, and this one in blue here. So for each of them, we find the smallest edge coming out of it, and the left connected component finds this edge 1235, and the right connected component finds the same edge 1235. So upon adding that, we get our resulting minimum spanning tree. After joining those clouds, we have one cloud consisting of all vertices in the original graph. So this is our minimum spanning tree using Baruvka's algorithm.